Listening and evaluating the recording of instruments and voice are the main tasks performed in a control room of recording studios. But in order to do a proper assessment, you have to have a favorable acoustic condition in the environment where the audio is played back. The conditions of this acoustic environment are analyzed using parameters that directly affect the listener. The audio monitors and the acoustic quality of the environment determine the quality of the audio being evaluated. The main objective of a recording studio is to register the music works of artists. The studio environment should be comfortable, cozy, quiet, and able to provide favorable conditions to create and register the art. The composition and recording process can be long and arduous. Minor changes in this process can make the song successful or simply fall by the wayside. The acoustic characteristics of a studio can mean the difference between a good or a bad recording because these features directly affect every step of the process from the initial capture of instruments to the mastering. The control room and audio monitors are the main reference for audio engineers and producers to monitor the audio to be recorded, or, in case of mixes and mastering or even editing, the audio that has already been recorded. One of the most laborious process in acoustic design of control rooms is achieving a balanced operation and room response curve in a large area of the control room, generating a large sweet spot. During the mixing process, the audio engineer, producer, in many cases, the artists are also present. That's why our sweet spot, must be as large as possible. This space usually varies according to the dimension and shapes of the room. Let's talk about the first control rooms. This subject was part of my research, and I think it can help us understand more about the evolution and concepts of control rooms. The use of acoustic treatment in recording studios began to expand in the 1950s with the growth of pop music and with the emergence of the stereo format. The control room in those days had only minor acoustics treatment and they were distributed randomly. At that time, it was very difficult to measure the acoustic parameters of a room. The equipment for measuring acoustic was rare, expensive, and was very heavy. Audio engineers built or designed their own mixing consoles, microphones, and preamplifiers. Everything was subjectively evaluated, and the final judgment was made based on the years of those engineers. Those early studios were treated with absorption by means of perforated plates, spaced away from the walls, containing mineral wool inside. This type of treatment is effective for medium and high frequency. There are no documents from the 1950s that reveal a treatment for lower frequency. This frequency region seemed to have had little importance during that period. As the stereo format grew, there came the challenge of designing a room with symmetry between the left and the right sides from the mixing engineer's position to provide a balanced stereo image. In 1956, Michael Redinger was hired to design the studio located in the Capitol Tower in Los Angeles. The studio had its reverberation time controlled for low frequency and also featured a variable reverberation time in recording rooms by means of acoustic panels. The control and recording rooms were large, allowing the recording of several instruments simultaneously in the same environment. In the 1960s, it was already possible to find acclaimed designers who were extremely important in the history of acoustic studios, like Tom Headley. Headley started designing rooms with suspended monitors and a large amount of absorption. At this time, most rooms were practically anechoic chambers where only the floor surface provide reflections. Since the primary function of control room is to acoustically simulate the residential environment where the final projects will be reproduced, this high amount of absorption is not recommended. Don Hitler at the time designed control rooms with certain acoustic features that are still used today. The monitors were embedded in the front wall, like flush mount speakers. The ceiling and the back of the room should not cause reflections, no first reflections, just like recommended today. Hitler's project already had high symmetry between the left and right sides, and the reverberation time was low also in the low frequency due to the high absorption in this frequency range. In his early design, he introduced a reflection canopy in the ceiling above the position of the mix engineer. It's normal to see, nowadays diffusers in the sides or just above us, above the mix engineer areas. In order to obtain a good absorption at low frequency, Hitler developed the bass trap, which are traps built to absorb low frequency. Bass traps are usually placed in the corners and the edges of the room because these, as I said before, these are the regions with the highest concentration of standing waves. In the 1970s, a huge effort was made internationally in order to create the ideal design for the control rooms. Tom Hidley of Wesley Audio introduced in the 1970s the project called Interchangeable. The reverberation time of this room was less than zero point 0.3 seconds. Many bass traps were incorporated trying to keep the reverberation of lower frequencies similar to the middle frequencies and also to lessen the effect of standing waves. The monitors need equalization in order to balance the frequency spectrum. Soon it was possible to notice that controlling the reverberation time and the time between the reflected and direct sound was not enough to describe the sonic characteristics of the room. In order to quantify the quality of sound in a control room, measurements of sound pressure level as a function of frequency began to be used. The measuring techniques was introduced by Richard Heiser at the end of the 1960s for other purposes. As is still common today, a pink noise was generated at each speaker and an omnidirectional microphone was positioned at the mix engineer spot. The measurement signal was analyzed in band of 1/3 of an octave, and this curve was called Hall's curve, which means the sound pressure level curve as a function of frequency. This measurement technique began to be used by Don Davis and Davis chips, and many others began to realize that early reflections generate an unwanted coloration which result in the comb filter. From this perception started a strong tendency to design rooms with a large amount of absorption. In 1975, Manfred Schroeder proposed diffusers designed to be used in environment intended for classical music, which had great results when used in recording studios. These diffusers were placed in the back of the room to avoid specular reflections and give the impression of bigger room. Just like I said, it's really common to find diffusers in the back of the rooms to avoid specular reflections. It can be keyword diffuser or whatever, skyline or any kind of diffuser. It's usually we see keyword diffusers, right? Schroeder's diffusers, and also we see in the ceiling and sometimes in the sides, right? In a place where you would have first reflections, all right? So sometimes absorption, sometimes diffusers, but never. You can't have specular reflections in the mixing engineer's position. All right. In 1979, Don Davis and Davis Chip presented an acoustic design for control room that became a reference and was used in most of the recording studios at the time. The name Live End Dead End was assigned to the design because one half of the room received a large amount of absorption treatment and the other half of the room was live, getting a diffuser such as Schroeder QID, for example. So I'll show here another picture, and we can see the front of the room. That it's called dead end. A lot of absorption here in this area. And here is the mix engineers area, the mix engineer spot. And in this example here, we have a lot of diffusers. Okay, so this is a keyword here, but it doesn't matter. A lot of diffusers. We can see in the back of the room. So this is the idea for, live end, dead end conception. The front of the room is acoustically dead in order to lessen the first reflections, avoid any effect that, unwanted effect, and allowing the engineer to hear the effect caused by the first reflections from the previously recorded audio, coming from the recording room. Since an anechoic environment should be avoided, the back of the room was responsible for generating the desired reflections. However, this should not be specular reflections. In the lead design, the room must be symmetrical between left and right side. Okay, we have absorption in the front of the room, diffusion, a lot of diffusers in the back, but between the left and right side, the room must be symmetrical. In 1982, ECM Mitsutani presented a proposal to AES convention in Anaheim as a solution to the dilemma of narrow listening room, where the outcome of an anechoic environment plus an echoing environment would be the new standard for control room. The design used large amounts of absorption in a wide range of frequency. This was possible by using panels and recesses with absorbent materials that were up to 2 meters deep. The reverberation time in this room was approximately 0.4 seconds. The rigid walls did not present any parallelism so as to avoid further echo. The loss of 2 meters depth on each of the 3 wall surfaces and the distance required to reach the low frequency absorption made these rooms very large and very expensive projects. The reflection-free zone started in 1984 from a group of designers and manufacturers of diffusers. The aim was to direct the reflections through the geometry of the room towards the speakers located in the back of the room in a way that all reflections were passed around the mixing areas. So no first reflections, okay? This principle is an extension of the LEDE, since the main intention in both cases was to lessen the first reflections and create good diffusion in the back of the control room. But the front area in this conception was devoid of absorption and conflict with the many major studios that were built following the LED concept. We had so many studios, especially in the 80s, maybe 90s too, built following the LED concept. The first reflections in the control room are also unwanted in order to be able to hear the original first reflections of the recorded audio from the recording room. The main argument to justify this principle was based on tests conducted using the technique of time delay spectrometry, or just TDS. Some authors has questioned this argument since the measurements were made with just a omnidirectional microphone intended to simulate the human hearing. Currently, we can find miking systems that emulate the human auditory system. This product contains two omnidirectional microphones with similar spacing between the two ears of humans. Those microphones are separated by a head, usually made of plastic material, and often with a torso made of same material. The name assigned to this capture system for measurement is dummy head. All right, so we can see here a picture of F RFZ. This is a RFZ zone, okay? A reflection-free zone where the engineer works, the mix engineer, producer, whatever, or master engineer. And here we have diffusers, okay? So you can see this picture here, an example of RFZ principle. Until the 1990s, United States stood out as a major contributor to acoustic solutions to be implemented in control rooms. The growth was motivated by large companies in the music industry, but between the years of 1992 and 1993, Europe made an effective contribution, presenting new proposal for acoustics treatment of control rooms. The BBC introduced the controlled image design concept. In this project, there should be no first reflections in the mix engine in the near area. Just the same way that the reflection-free zone and LEDE principles. The main difference in this case, in this solution, is that the targeting is totally geometric. Since there was little treatment for absorption, the reverberation time presented values between zero point 0.3 and zero point 0.4 seconds. For the first reflections, after 20 milliseconds, the level should be below 15 decibels at the mix engineer's position, the reference listen position. One feature in that room model is the small amount of absorption, which looks very similar to the location where the finished audio is usually playback. I mean, our home or places with not that much treatment, which receive no specific treatment for reducing reverberation of low frequencies. The implementation and design of this type of room is not simple. Its main advantage is to work well with near-field monitors. The difference between the design and the design of reflection-free zone is that this type of control room is also considers the use of small independent monitors, which are not embedded as an alternative means of audio monitoring. Specific room, big treatment. In all design chronologically present, the control room had diffusers and specular surfaces reflections that made their sound unique. Even the rooms that were built using the same design had different sound depending on the material and the amount of diffusion or absorption and its geometry. In the 1970s, Tom Hitley and Philip Newell began using a room design that Newell presented in 1991 at AES convention through the article Non-Environment Control Room. In this type of room, the side walls, ceiling, and the bottom receive a large amount of absorption material. The bass traps were reintroduced by Hitley, and since they were big, they could act on low frequency down to 40 hertz. Only the front wall of the control room was reflective, which provide a very low reverberation time to the environment, make the characteristics of the room interfere very little in the monitor audio. This design is called non-environment room. As this high amount of absorption is involves high cost, few rooms were built using that format. These rooms, although unrealistic in comparison to homes environments, were where the final audio will be heard don't provide diffusion and acoustic reflections of the monitor audio, allowing the audio engineer to hear only the sound coming from the speakers. The monitors were positioned on the front wall, but the geometry of the room redirected the reflections to the rear without reflecting into the mix engineer's area. The idea was the front wall, the floor, and the equipment to produce the reflections in the room to make it not overly absorptive. Although the direct sound increased in relation to the sound reflected by decreasing the first reflections, Tunnehill design is very expensive due to the large quantity of absorption materials. The forerunners of this attempt at standardizing the acoustic design in control rooms were the broadcasting companies, due to their constant need to monitor audio in different locations. The recommendation for this type of environment was to emulate the residential environment, since the consumer would listen to the program's CD and other medias at home. The problem with this concept was that the recording industry extended to the whole world, where local architectures vary as to things like size and format, which makes standardizing a residential environment impossible in many countries. Through a great effort, the audio industry and broadcast companies proposed a new standard for control rooms in order to establish acceptable values for control for parameters evaluated. This standard is the EBU TAC, Technical Recommendation 3276, Listening Conditions for Assessment of Sound Program Material. It was published in 1998. This recommendation describes requirements for dimensions and proportions of the room, the limit values for reverberation time, frequency response, sound pressure level of the audio on the monitors for measurement, and sound level in the early reflections. The anechoic concept was designed around the year 2000 by George Messenberg, the author of the article that present the parametric equalizer at AES. This type of room involves a complex array of huge number of diffusers and absorption for lower frequency in the corner of the room. As we can see in the Nashville Blackbird studio, I'll show a picture here. We can see a picture from the studio. It's a Studio C. A lot of diffusers, a lot. The absorbers in the corners of the room are to control the lower frequencies, since the diffusers that act in this frequency range are very large and can change the balance of the acoustic modes of the room. Measurements carried out in the Blackbird studio by impulse response showed 30 decibels decrease in the early reflections. That's a lot, you know. Technical recommendation tell us about 10 decibels. This concept room is called anechoic because the reverb level is very low. Sensation similar to an echoic chamber, although the decay is of 0.3 seconds, near to the upper limit of 0.4 seconds set by EBU. There is no sense of reverberance, generating a very precise acoustic image. It's another concept, it's another technique. It was in 2010. Bogi Petrovic and Zorika Davidovic present a new acoustic adaptation method for control rooms that received the name of My Room. This type of room is treated with a large amount of absorption. Again, for low frequency, added to diffusers. Those efforts achieve a good result in balancing the frequency response spectrum in each of the two rooms evaluated in the publication. They had a publication, as I said, in AES. It was 2010, right? Although the width and height have values that were very similar or equal, which provide axial modes in the same region. In the two rooms they studied, The first reflections were 20 dB, 20 decibels below the direct sound. The treatment was made using joint diffusers based on the Schroeder's principle and absorption for the lower frequencies. In this case, the lower frequencies are not scattered by diffuser, but are absorbed by the absorbers that are abundantly laid out in the control room. So I'll show the picture here. I think it's a truck. Let me see. And we have QRD diffusers, the principle, and a lot of absorption, like here, okay? It's like a bass trap, you know, almost like a bass trap. And we have diffusers here, and as we can see, air between the woods, which can pass through. Okay, so we have in here this picture showing the my room principle.